Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, so we're very happy this week to have Esha Ghosh visiting us from Brown University. So Esha is a PhD candidate, and she's been working in intersection of privacy and security and applied crypto. And today she's going to talk about some of her work on authenticated data structures and adding zero knowledge.
Thanks, Melissa. So today I'm going to talk about our work on efficient zero-knowledge authenticated data structures. So this is a brief overview of the talk. First, I'm going to tell you why this field of study is important. I'll motivate this field of study. Then I'll tell you some traditional authenticated data structures that actually do not give you the support for privacy. Then I'll give you first an informal and then build up the formal security definitions that we proposed. And finally, I'll give 3 different constructions for 3 different data structures, and this section is completely modular. And finally, I'll conclude. So with the advent of cloud computing, a large number of corporations and individuals outsource their data and computation to this untrusted cloud storage or server. It is a very common thing now, and since the data is now the owner who owns the data is not in physical possession of the data anymore, it is stored on an untrusted server, there is obvious question of integrity, as in that the data has not been tampered with and it has been maintained properly. But along with that, often third-party providers are given partial access to this data, which introduces another problem of privacy. So that they have partial access and partial view of this data, but to prove integrity, often this more information is leaked about the data than they should learn. So this is more than a theoretical risk because there have been serious attacks in this. So I'm just going to give you a few motivations. So one is called the zone enumeration attack. It is an attack of DNS name resolve queries, where DNS queries are basically give me the IP address of some host name. And the way the zone enumeration works is an attacker gets to know all the IP addresses of a particular zone, all the host names of a particular zone. So how does it work? So this, the owner of this zone, it generates, first of all, let's call this, there are 2 kind of resolvers, primary name resolvers or secondary resolvers. So when a query comes that give me the IP address of this particular website, this resolver gives the answer that this is the correct, this is the IP address. Now in 90s, early 90s, DNSSEC was proposed to defend against attackers, so that you know that the correct IP address is being returned. These addresses are usually signed by the trusted owner. And then there is this issue, but then there are zones that are not. The queries can come from an arbitrary website corresponding to which there is no IP address in the record. So you have to also prove to the querier that that result is not in the database. Now proving the positive, so there are 2 kinds of queries. One is positive membership, another is non-membership or negative membership. So proving positive membership is easy. You can, in the offline phase, the resolver can just sign all the pairs that are in the log and store it even with an untrusted server. So this setting is very important because often the authoritative name servers that administers a zone, they do not, they have secondary resolvers. For example, if you do an NS lookup for brown.edu, 3 of the name resolvers are owned by Brown, 1 is actually owned by UCSB. So what happens is the secondary resolver can also answer these queries, and they need not be trusted. They are secondary resolvers, they do not administer the zone. So in the problem here is how to prove the non-membership. The membership proof is sort of easy. You just sign it offline, or the authoritative name server signs it offline, and the secondary just gives the signature, and that proves membership. So there have been a few ways proposed for non-membership. So the most recent one was NSEC 3, which basically says hash all the website names, generate these hash values, then sort these hash values and sign every pair, okay, and store this record with the secondary resolver. Now, when a query comes, say q.com, which is not in this list of data, the proof is the hash of q.com is computed, and let us say the hash falls between these two records. So, it is sufficient to return this two records sign, and that will prove that that zone is not in the database. That was the proof. Now, what is the problem with this proof? Of course, there is this dictionary attack and the zone enumeration attack. So, what an attacker can do is, it can take ask many arbitrary queries and collect all these hashes of the zones, and then mount an offline dictionary attack on this. So, this is a scenario where privacy is really important, not just integrity. Okay. Another example is where public audit of digital, yeah, please. Yeah.
So why shouldn't someone be able to see the list of all the domains and IP addresses?
Oh, this is a privacy issue. Like you are going to learn all the host names in a zone. That could be a privacy preserving thing in itself. You might know all the host names, the router names and everything, and that is a base to mount more complex attacks.
Okay. That's not information I can learn by scanning.
No, you have to learn. You have to ask what is my IP address, and then you learn all the host names in that zone. Okay, this is the question about digital records are often subject to audits, or authorized parties or analysts are given access to it when something malicious goes on. For example, the database, the email record of a particular company, it is often stored with a third party server, and in case of some sort of fishy activity between certain dates, in this example say this date period, authorized data analyst is given access to records from within this time period. But because of privacy issue, again here there are again the requirements are twofold. First of all, you need to prove to the analyst that this server hasn't tampered with the messages, it is returning the correct messages that it got from the organization. But also because of privacy reasons, it is necessary not to reveal anything beyond this time period and the data. And finally, this is another example where XML data is stored as directed trees. So, for patient health record, for example, and the insurance company might have access to certain portions of the tree, and to prove integrity, you should not reveal anything beyond that subtree wherever it has access. This is some motivating examples. So, this scenarios motivates the following model. Okay, so this is a three-party model where there is a owner, a server and clients. Okay. The owner is a trusted owner of the data set, somebody who trusts to generate the data set and give some authentication information on it. Now, this data is stored on this untrusted server. So, the adversarial model here is that the server is not trusted to store the data faithfully all along. It might delete, or it might get omitted, might get attacked, but so there is a, okay, I will come to that later, but the data is stored with the server. So, the owner basically generates some sort of authentication information about this data set and stores it with the server. It also generates a short succinct digest of this data set and makes it publicly available. Okay. And then the owner can store and periodically update, but otherwise owner goes offline from this scenario. Now, the clients interact with the server to ask queries on the data set and gets responses. Here the requirements is that first is integrity, where does the client never accepts incorrect answers. So, whatever the owner has generated, the server cannot give some answer which is inconsistent with the data stored, generated by the owner. And the privacy requirement is that the client does not learn anything beyond the answer of the query, anything else about the data set. Okay. So, if you are familiar with traditional authenticated data structures, traditional authenticated data structures gives you that guarantee that of integrity, that data is not getting tampered. But these proofs are generally leaks a lot of information. So, for example, this is a very well known data structure, Merkle's hash tree. So, when you prove integrity in Merkle's hash tree, for example, you want to prove this the integrity of element x2. So, the authentication path are these red nodes, which reveals a lot of information. First of all, it reveals the number of records in the database. And if these data elements are sorted, stored in sorted order, it also reveals the rank of the element. So, there is a lot of leakage that happens with the proof that this is indeed in the database. And the way non-membership proof is proved is if they are ordered like we just discussed in the hashes, you give two neighboring elements, and that also reveals a lot of information. So, this is not privacy preserving. Okay. So, this is another data structure, authenticated skip list, which again reveals a lot of information. This is to say that the traditional ADSs do not give privacy, the zero knowledge privacy. Okay. So, now I will come to the formal security definitions. So, if you have any questions at this point, it would be good to ask. Okay. Okay. So, the algorithm, there are three parties like we said, the owner, the server and the client, and there are three algorithms. One is the key generation algorithm that takes the security parameter and generates a secret key and a public key for the owner. Now, in the setup phase, the owner has its own secret key, it takes the database D0, let us say at timestamp 0. It generates some succinct authentication information, the little orange box that we saw, that will be publicly posted, anybody can access. Then there is theta 0, which is the authentication information that it will store with the server to basically facilitate answering queries, and some state information, internal state information that it will use if it ever wants to update the database. Okay. So, in the update state, it just takes all this information, the database snapshot at some time I, and this is the update string uy, which it wants to update on the database. For example, if it is a set, maybe it wants to insert a new element or delete an existing element, and it gives you the updated database, the updated succinct signature sigma I plus 1, some update string that the server will use to update things at its end, and updates its own state information. This one?
That's later.
This one?
I don't see theta I plus 1 on 1, but I guess that's.
Oh, that is the server. So, the server as of now has theta I. So, it will take this update string and update it at its side, which is this. Okay. It takes that update I, updates the database, and generates a theta I plus 1. Now, so the server is responsible for this perform update and query algorithm. This is in query algorithm, it has this sigma j, which is public information, everybody has. It has theta j with corresponding to the database j, and it receives a query delta from the client. Okay. And it generates an answer and a proof. So, the rest of the information it has from the owner, only this is the online information that comes from the client, and it generates a proof for that. Yeah.
So going back to the fact that
This one?
the update takes theta I, does that mean it needs to get help from the server and storing data to compute this little update I thing?
It depends on the implementation, it could even have it in its state information. So, it just needs to know what was the last state the database I was in. Okay. And in the verify phase, the client just takes a public key, the sigma j, and the query, its answer and proof, and either accepts or rejects. Okay. So, like we already described, the security features are twofold. Completeness just means that correct answers will always be accepted. The soundness is the game that models the adversarial behavior of the server. So, in this game, the adversary initially sees the public key from the challenger, and it comes up with a database of its choice, call it D0. It gets the information that an honest challenger would do, an honest owner would go, sigma 0 and theta 0, and then some polynomial number of times it asks some update information of the database and gets the update strings. Okay. And finally, it outputs some answer which is inconsistent of the database snapshot j, one of those snapshots through which it has queried, and it wins if the answer is accepted even though the answer is not correct with respect to the database. Okay. So yeah, notice that the server actually in the original scheme protocol, the server doesn't do the updates, but this is a stronger server who can also affect the updates. So even that, even when the updates are adversarial, it should not be able to forge this.
I forgot what's the sigma I.
This one, this is the succinct public information about the database. That's public, yeah. Okay.
So that's the model where so the idea is that the owner of the database updates the database and then publishes its new sigma I.
Yes, exactly. Yeah, you should not be able to learn from it. Yeah.
So like, what is the, I don't understand the role of this sigma, like what public information?
It is some sort of succinct commitment to the database by the owner. So because the server has to prove correctness with respect to the original database, but it does not know the original database, so it is consistent with respect to the succinct commitment that the owner generated.
You mean the verifier doesn't know
The verifier doesn't know, yes, sir. Yeah.
server knows.
Server knows, of course, yeah. The verifier doesn't know, yes. Okay.
So is the previous definition, is that a standard definition?
No, these are the definitions we proposed for zero knowledge authenticated data structures. There was no formal study of this. Okay. And then there is the privacy definition, which models the adversarial behavior of the client or the verifier. So here the client is adversarial, or the adversary is modeling the client. So the adversary initially sees it model as it's either talking to the challenger or it is talking to a simulator, and it will succeed if it can tell with non-negligible probability over half who it's talking to. So the idea is these views should be indistinguishable to the client, to the adversary. So the adversary initially sees the public key, which comes from the challenger or the simulator. Then it comes up with a database of its choice, some adversarial database, which is sent to the challenger if it were talking to the challenger, but simulator sees nothing about this database. And then it sees this succinct sigma 0 that the owner would generate. Simulator also simulates that and shows it to the adversary. And again, then the adversary asks two kinds of queries. One is query, one is update. So if it asks a query, it gets from the honest challenger the answer and the proof. And in case of the simulator, it only has Oracle access to the database, meaning that the simulator only receives the answer to this query with respect to the most current database from the Oracle, and it simulates the proof. So answer is the only part the simulator gets from the database with its Oracle access, and this is the part proof that it simulates. And if it is an update query, then the honest challenger obviously sees the update and it updates this sigma. But for the simulator, it doesn't see anything except a validity bit, meaning is this a valid update on the current database? Right? For example, if it's on a set, it's trying to insert duplicate, that's not a valid update. So it only receives a validity bit, and assuming it's a valid update, it gets sigma I plus 1. In both cases, if it's an invalid update, it gets bored or something.
So for the queries, the simulator gets to see the query and the answer, but he just doesn't know the data structure.
Yeah, it doesn't need to see the query also. It only needs to see the answer to that query.
Yeah. See like what type of query it is or something like that?
It's, well, yeah, it should know the protocol. Yeah, yeah. That it needs to see, yeah. Okay. Okay, so that was about the model. Now I'm going to move on to the next part of the talk, which is specific constructions for some specific data structures. So these are the three data structures I'll try to cover. The first one is very simple. It's set membership and non-membership. So this, I guess, I don't have to go over this. So, yeah.
Can I go back to the definition again?
Yeah.
So you should have to know the simulator should have to know the query because he has to come up with a proof that verifies for that query.
Yeah, well, the simulator has to know the kind of query, yes, but it's already defined by the ADT, the abstract data type on which it's doing.
But I mean, shouldn't query? 'Cause it's going to produce an answer. Well, it gets the answer from
It gets
from
the
this
answer
oracle,
and it simulates.
but then it has to simulate a proof for a particular
query.
statement, right? Because the verifier is going to be verifying this proof with respect to a particular query and an answer.
Okay, yeah, yeah, that's right, yeah. It needs to get the query, right, yeah, okay. Yeah, it needs to get the query and, right. It, just not the database, yeah. Yeah. Okay. For set membership, it's based on bilinear maps, the construction. So this is just the notations. And so for the notation, let's say chi is a set of elements. Okay, this is the data base, and the edit is, so the client query is an element X in the set or not, in the set chi or not, and the server's response is a bit, which is the answer, yes it is in the database, or no it is not in the database, and the corresponding proof. Okay. So for a set, we will first represent it as a formal polynomial. You could write minus here also, it does not matter. And the polynomial is called characteristic polynomial of chi. This is the formal polynomial. And when, sorry? That's a product, yes. And when this is evaluated at a secret point, we just denote it like that. That's a value, right? Okay. So this is the construction for the key generation and the owner. So these little red things denote the number of operations, group operations it's doing. So first you generate the bilinear public parameters. So take this bilinear group G1, we are doing it a symmetric group, symmetric bilinear pairing, the bilinear map, and this is a generator of the group G. And this is the prime order of the group. So you choose a secret S from ZP star randomly, this notation is to say it's random, and set the secret key as S and the public key as G to the S and these parameters.
What is this G1? That's
it's a bilinear group.
So it's the group where the
yeah. Okay. Now in the setup phase, it takes this, the owner again runs this set. So the additional thing it does is chooses a random R from ZP star, which is the blinding factor really, and it sets as sigma 0 G to the R, the characteristic polynomial evaluated at S, the secret point. Okay. And then theta 0, remember this is the auxiliary information that is stored with the server. So this is this long public key, it's not the public key, like this tuple and the blinding factor and the set size. Anyway, the set is stored, so this is not important. And for this talk, let's say the state is the set that is stored, in case it needs to update the set later. But you can do other things like this can also be outsourced, and you can use a Merkle tree to just keep the root to know the state of the set. But for simplicity, let's say the state is the set that it stores. Okay. Now the query part. So for the query part, the server has some snapshot of the set chi j, some theta j, and this is the query delta. So if delta equal to x is in the set, okay, then the answer is 1, and the proof is this sigma j to the 1 over s plus x, which is basically this polynomial. Okay. So the server computes this and returns it as proof. Okay.
Are you going to talk about how you can actually compute that with the polynomial?
I'm not going to talk about it, but this is a polynomial with, it is just a characteristic polynomial with one factor missing, it's degree n minus 1 characteristic polynomial, but the server cannot compute it, cannot compute this polynomial and raise g to that, but it has this string g to the s, s square, s to the n, so it just basically raises it to the correct coefficient, and that's how it computes it.
So it like recomputes it?
It computes it. It was not computed earlier. So what was computed earlier was this without this factor s plus x divided.
Yeah.
Okay, so that is,
That's why the complexity is, and
yeah, that's why the
depends on the
complex.
size of the cell.
Yeah, it can be done at F15 first time n log n. Yeah. Okay. And then if the set is not in the set, the way we prove non-membership is, think of the characteristic polynomial of x plus z. This is a degree 1 polynomial, right? If your set were only the query x, then z plus x will be its characteristic polynomial. Now, if this is not in the set, then this polynomial and this polynomial might be co-prime to each other, meaning that it cannot have a common factor, common divisor. Okay? So, the way then this is done is run extended Euclidean algorithm to generate the coefficient polynomials. The server does that, Q1z and Q2z, and what we actually want to give is g to the Q1z and g to the Q2z. That will prove that it's non-membered. The verifier can check in exponent using bilinear map that these are co-prime, but this is not perfectly blinding. So, we have to additionally do this step of pick a fresh randomness, which the server does, and blinds this Q1 prime and Q2 prime, make it Q1 prime and Q2 prime, and return this as non-membership witness. So, the non-membership witness is two elements, W2 and W2. Okay. Yeah.
So why is there an R in grade somewhere in the
Oh, because there is this blinding factor R in the original accumulation. So, you sort of have to cancel it out to say the verification goes through. So, if you, yeah, so this is the verification, right? When you do the pairing, you have to take that R off. Yeah, that's all. And that the verification is obviously simple. You just, for the membership witness, you plug that witness, right? So, this is run by the client. So, recall that the client has this and this from the owner, client gets this from the server, and then it can compute this part on its own, and it plugs in and checks if this equality holds for membership. And for non-membership, it basically checks that the extended Euclidean, the GCD is 1 in the exponent. So, what this gives is g to the Q1 s into characteristic s plus g to the Q2 s into characteristic s, and it equals 1 in the exponent. Is that clear? Yeah. So, this is the equation that you want to check in the exponent, right? So, yeah. And these gamma factors are set accordingly so that they cancel out in the exponent, and you can verify this. Okay. And the update algorithm is also really simple. That's done by the owner. So, if a new element is added to the set, it just refreshes this sigma I with this new factor and blinds it with a fresh randomness. Okay. So, it's like S plus, let's say x was not in the set earlier, and it's adding this new element to the set, the owner. So, the owner takes the old digest and raises it to s plus x some r prime, the fresh randomness. For non-membership witness, if it wants to delete something, it just takes off that spot from the set. That's all. That's the update. Yeah, and perform update is very simple. It's just refreshing with this new r prime on the server's end and the sigma.
Does the server actually need R? Could you multiply it into all of
The server needs r and r prime, yes. Because the earlier one was just r, now you have blinded with fresh randomness r prime. So, now the randomness that is in the exponent is r prime. Yeah.
So then, should that be an n prime in the last bullet? G to the s n prime?
Well, yes, and yeah, if n prime is larger, it ever grows, it takes one more factor, right? Yes, exactly.
So that would have to be in the update string.
Yes, it's in the UPD string, yes. Yeah. Yeah, I'm not going to prove it here, but the proof is based on n-strong bilinear Diffie-Hellman assumption, which basically says for a PPT adversary who has access to these public parameters, it is hard to invert in the exponent. And that's what the proof is based on, it's intuition. Okay. Now we're on to the next part. Yeah.
Are you giving intuition for why zero knowledge?
Oh, why it's zero knowledge is because every part that the client sees has a proper blinding factor. So what does the client see? It sees the public key, but beyond that, whatever it sees about the database, the succinct sigma that it sees has this blindness in its exponent. And the way we constructed the proof, every proof also has a, every proof also has randomness.
Although they're correlated. You may see many proofs for the same database, so then it will all have the same R.
If you see different proofs from the it will be the same R, but it's that correlation is already known to the client, right? I mean, you're not trying to hide, there's no unlinkability property. You're not trying to say that it's not from the same database.
So is it something like you're showing that the proof you get is exactly the one value that satisfies the equation? That's a random.
No, it's just the randomness thing. Yeah, it's not that. It's.
So the randomness is fixed when you set that sigma j.
So are you asking about the soundness proof or the?
No, the zero knowledge proof. So the sigma j should.
Yeah. So the simulator can just pick any randomness and say g to the r is the sigma. Right, and whatever proof comes, it just divide it accordingly.
So you say you can pick s's at random.
Yes, at the beginning.
Honestly,
Yeah, exactly. Yeah. And these witnesses you can generate with respect to the initial randomness that you picked.
Okay, so you pick s at random, you pick
R.
r times the characteristic polynomial, really just as one random.
Just one random, yeah.
Another characteristic
Yeah.
polynomial because you're on set, and then
And then you just divide it when you want to prove membership.
and that works because this is the only thing that will satisfy the verification equation once you fix sigma and then query.
Sorry?
That works because that would be the only thing that satisfies the verification equation. Like once you fix sigma, there's only one.
There's only one degree of freedom. Yes, exactly. Yeah. Okay. Okay. So for the next part, I'm going to talk about range queries, and here the problem is the data store is a key value pair store. Okay. So keys are from a totally ordered universe, and the client query is basically return all values whose keys lie within some range A to B. And the server response is the answer, which is the correct key value pairs, along with the proof that this answer is complete, that all the elements that it had returned were really in the database and it has not omitted anything. Like an example, this is actually from the Enron email dataset on which I ran experiments for this query. So you can think of this as the date or timestamp, and this is the mail ID. So if you think of the database, there are many possible timestamps, and in some timestamps the data, there are mails, others are empty, nothing is in there. So this is basically your range, the domain set 0 to 15, and some of this is the data store, which are these 6 records. Okay. As you can see, the 6 records are present, so only these keys are present in the data set and rest of the keys are not present in the data set. So let's try to see how we could think of a simple solution in this case. Do you have any questions? Okay. So the one way to prove this could be that we initially, what we were talking about, this idea we have already revisited a bunch of times. So the key value pairs that are present in the database could be signed by the owner. And to prove that the things are not present, the owner could also sign the adjacent pairs, right, of the keys that are present. So one one signature could be for 0, 1, the keys that are present, and this pair, and then this pair, and so on. So to prove that something is not in the database, you can give the corresponding, the server can provide the corresponding signature. But this obviously violates privacy. Okay. Now there is an attempt too that you could think of, like why not, from the solution we saw in part 1, why not accumulate the elements, the owner maybe computes a zero knowledge accumulation of the elements that are present in the data set. And then when a query comes, the owner proves in zero, the server proves that these are members of the database the owner had accumulated. And to prove that there are no elements, it proves non-membership in zero knowledge using the accumulator. But the problem here is this range could be too long, corresponding to the number of data sets in the database. So for example, if the key in this case is a 4-bit string, there are 2 to the 4 possible keys, but only a very few are present in the data set usually. So if you want to prove non-membership, you have to do so much work, you have to touch every possible element that's not in the data set. So that's not a viable solution. So let's see what we can do then. This idea that we used was of hierarchical identity-based encryption. Okay. So the idea here is anyone can encrypt messages for users using their public IDs, and the users will be able to decrypt only if it possesses the correct secret key. Okay. And this I am going to tell. So implicitly you can think of a hierarchy as a binary radix tree, where the root is empty and the left child is marked with a 0 and the right child is marked with a 1, like this radix tree. Okay. So if the ID at level k can issue secret keys for his descendant IDs, but nothing beyond that. So if somebody has a secret key for this ID, it will be able to generate secret keys for every ID that's below it or it's in that subtree, but will not be able to generate anything outside that subtree. So the idea is if a message is encrypted with the ID of 00, 00 can itself decrypt it, or it can generate secret keys for any descendant who can decrypt it, but nobody else will be able to decrypt it. Okay. Okay, so now the idea, now we are back to our range queries. So think of the database that we were initially thinking of. Okay. Now these key value pairs are present in the data set and the rest of them are not present in the data set. So think of this implicit radix tree and delete all the leaf to root paths for these keys that are present in the data set. Okay. So you end up with a forest which has basically this orange nodes. Okay. So what the owner does is the owner generates signature for all the key value pairs that are present in the data set and sets up a hierarchical identity based encryption scheme of that height of, in this case, 4-bit of length 4, and it generates this secret keys for the roots of this forest. Okay. So this is the setup phase and these are stored with the server. Now when a query comes, let us say the query is 4 to 14, that is the client query phase. The owner, the server first returns this deep yellow key value signature pairs, those are the databases that are present in the data set. So it returns this to the clients. Okay. And for the non-membership, we have to first let's look at this idea of canonical covering for a range. What does it mean for a canonical covering for a range with respect to a tree of certain height, say L. So the canonical covering is basically a bunch of nodes in the tree which satisfies the following properties. First is that every node is a descendant of one of the nodes in the canonical covering, and the second is every node's leftmost child and rightmost child falls completely within that range. and this of given height, of course, given a tree and a range, this covering is unique. So, in this example, if 4 to 14 is my queried range, this is the canonical covering, the roots of this forest basically, this one and this one and this one. Okay. Now, since this is unique, the client can compute it on itself, right. Now, the client computes it on itself and it also has got the signatures of the elements that are present in the data set. So, it computes this canonical covering and deletes those paths from this forest, the red paths it deletes. So, it is left with this forest, the blue forest. Now, the client takes random messages and encrypts them with these IDs, the blue IDs, and sends it to the server. Notice that because of the way the setup was done, the server either possesses all of these corresponding secret keys or it is able to derive the secret keys. For example, in this case, recall that the server did not have the secret key for this one, but it had the secret key for its prefix. So, it can generate the secret key for this and then it is able to decrypt it. So, if you are able to decrypt it, you can send it back and if they match, the client accepts. So, that is the, and you can replace it with the signature, hierarchical identity based signature instead of encryption, and that is the complexity. Yeah. This is a comparison with the previous work. So, the only previous work known for this was from ICAP 2004, which was a long time ago, Ostrowski, Rakoff and Smith, and that was a stateful algorithm. It was very inefficient with generic proofs of zero knowledge. Okay. Okay, so yeah, and the security is based on the unforgeability of the, sorry, this is not aggregate signature, of the signature scheme and the high security. Yeah, yeah. And I have 5 minutes. So.
Yeah.
Okay. So the last part of the talk is order queries on lists. So here L is a linearly ordered list of elements, set of elements, and an order query is a pair from the set, and the answer is X and Y rearranged according to their order in the list and the proof of the order. Okay. And we will use aggregate signature for the scheme, but if you know this, I am going to skip this slide. Okay. So the aggregate signature is this idea of given signatures or n distinct messages by n distinct users, you can generate a short succinct signature sigma. So given the signature and the public keys and the messages, the client can be convinced that they were indeed signed by the correct users, and we will use a special case of a single signer instead of n different signers. For n messages, we will use a special case of a single signer, and it is valid only if the aggregator used all of the sigmas. That is the security of the aggregate signature. It cannot give you a spurious signature and aggregate it along with the other signatures. Okay?
Is there an order?
No, it's just, yeah, it's just a set. Yeah. I'm going to use this, so I just talked about this. Okay. Now for the list construction. So what is the basic idea of the list construction? It is that for every element in the list, we are going to associate a member witness with it. Maybe the picture is better. So if you have this set x1 to x4, for every element there is a member witness, which is some blinded version of the information of its rank in the set and the element itself. Okay. Now the owner will initially generate this list identifier to say that this is unique for the list. It will generate a member witness for every element in the list and sign them individually, okay, and aggregate them to form the list signature. Okay, and this will be stored with the server. And the sigma, the succinct sigma that the owner publishes is its public key and this list digest signature.
Okay, so you're signing the position and the value.
Yes. Yes. Okay. So this is simple. How is this done? Two secret keys are chosen. The public key is just G to the V and the public parameter of the scheme. Okay. Yeah, I think I'm going to skip this for the sake of time, but the basic idea is this. So you pick fresh randomness for every element in the set and then compute this member witness as G to the S to the I into Ri. Okay. I mean, this is the bilinear public key G to the S, S square, S to the N. So this I index is encoding the rank. So for the ith element, the owner computes member witness as G to the S to the I into this randomness Ri, blinds it with randomness, then it signs it, hashes and signs this. Okay. These are all signed together to form this succinct signature, which is the aggregate signature. And then this sigma L is basically all this member witness, sigma I and the salt. This information is stored with the server. The authentication information that's stored with the server. Okay. Now when a query comes, the order queries to actually prove that some element precedes another, X precedes Y, these order witnesses are computed by the server online. These are not computed by the owner. So the only work the owner did is proportional to N, the list size, that's all. Now these order queries are actually computed, this is to prove that it is a part of that list. So it initially the server generates a signature for the queried elements only. This is because of the homomorphic nature of aggregate signature. Okay. And some verification info which I am going to skip for the sake of time, but this part essentially proves that this signature and these two together gives you the list digest signature. It proves it's a part of the list. And the order witness is more interesting. So the order witness that is computed basically it's a blinded version of the distance between these two elements. Okay. So it is computed as follows. Let the element rank be I prime and I double prime of the queried elements, and the distance that between them is I prime minus I double prime. Then the way it is computed is G to the S to the D, this is the distance, right, between element 1 and 2. Okay, notice that the server has this from its public key, right, it has this whole big tuple G to the S up to S to the N. So this into R1 into R2, the corresponding randomness that the owner had originally used to compute the member witnesses.
Was that given?
Sorry?
Was that given as part of the?
It was given to the server, yes, yes, yes. And then it just generates those order witnesses. Okay. So the verification is first verify this digest signature is correct, and then this is the verification essentially. Yeah. Okay, so this is the idea of the verification. So remember the member witness encoded the rank information in a blinded way. So the client in a blinded fashion checks this equation basically, that rank of x1, when the queries are x1 and x3, it checks the rank of x1 plus the distance equals the rank of x3. So that's just the check. So this is the order witness that the the server had computed. These are the two member witnesses that were computed by the owner that it had got, and it verifies that this equation accepts. Signatures on these two things, yes, on these two things. So again, the degree of freedom is 1 here. Yeah, this is a complexity which is really proportional to the answer size, it's optimal. Whatever is the answer size, the client does work proportional to that. So it's like really no more work. And yeah, the proof is based on this and bilinear Diffie-Hellman inversion assumption. So the intuition is that if the server had to cheat, it had to compute 1 over S, EGG raised to the 1 over S, and therefore it cannot, while computing the order witness, that's the reason it cannot cheat. Of course, unforgeability of the signature along with that. And finally, Okay, so this is a static construction. So we have a dynamic construction over this, which is from this version, the observation that even though this construction used rank information, we really did not need the rank. What we need is something that respects the rank order. Right? You could use another mapping to a larger domain. Instead of 1, 2, 3, you could say 5, 8, 12. So that idea gives, there is this well-studied data structure called ordered data structure that helps you maintain these tags when the tags are coming online. So we use this data structure to make this dynamic in a privacy preserving way. Yeah, and that's it. The conclusion was that we initiated this study of privacy preserving authenticated data structures, and the real takeaway from this work is really privacy and security along with efficiency. That has been the major motivation of this line of work. And these are the papers I talked about, portions from this paper, all are available on ePrint. And of course, you're welcome to talk to me about them, and thank you.
So in the first one, the set, the construction hides the size of the set.
Yes.
So if you were to relax it and say, I'm okay with making that, does the problem get suddenly much easier? I know like these original zero knowledge sets were really, the constructions were super complicated just to hide the set size.
Right. There are constructions that reveal the set size, which is pretty much in the same model. Well, the soundness is not as strong as that because they are really not considering update, but there has been results which reveals the set size and could do the same construction. This was published in TCC last year. So, yeah. It's not from, sorry?
Was it more efficient than constructions that do hide them?
Yeah, it used a form of signature, so it was more efficient than doing proportional work to the set size. Yeah.
And then my other question was for the range queries. So the privacy there, like you don't want to leak anything more than
The range.
queries, but can't, a handful of users after making many queries sort of know the whole data structure?
Well, the idea is controlled disclosure. So yes, if there are colluding clients who have access to the entire database, then you cannot hide anything, right? Of course, they will learn the entire data set if they collude. But the idea is the controlled disclosure so that the proof doesn't tell you more than that. So if you were to only query the database, you will not learn more than that. That one?
Yeah. Yes. Data structure. But, how much do you have to extend your domain sort of?
It's double the size. So if you were to allocate a set of size n, you allocate space for about 2n data sets and generate tags so that you can keep on generating these tags, which are like ranks, which as long as the number do not fall below n by 2 or 2n. Or go above 2n, and then if it happens, then you basically rebuild the data structure. So this is an amortized guarantee.
So the idea then is because that affects the size of your data that you have to give the server, the authentication data.
It does. Yes, of course it does.
So
Yeah.
you would just completely recompute that from scratch every time you have to change the size.
Yes, you have to recompute it. That's right. But because you have the amortized guarantee, it doesn't happen too often.